So I have a positive particle over on the left moving to the right with speed v, and there's no gravitation here to worry about. We have parallel plates, and you can see we have an electric field that's pointing down. However, what we are after here in this problem is creating a system where this charged particle on the left-hand side, as it moves through the region of the parallel plates, we don't want its velocity to change in any way. In fact, we want it to travel in a straight line, something like this. So it enters right here. I guess it would be a little bit below that. And we want it to travel totally in a straight line and not have no deflection. So we need to do something. As it stands right now, that won't happen. As it stands right now, this particle will be deflected down, and it will follow in a familiar parabola, just as if we were to throw a ball horizontally in a gravitational field. So pause the video and see if you can figure out what we could do with another type of field, not an electric field. So I'm not allowing you to change the electric field in any way, and I'm not allowing you to introduce another electric field. But what could we do with another hint type of field that we've learned about, such that this particle would just go straight through? Okay, pause the video and see if you can answer that question. All right, so you've done some thinking, and hopefully you realize that we could place a magnetic field also in this region of space. But we would need to have that magnetic field be in the correct direction so that it creates a force that's going to be equal in magnitude but opposite in direction from the force that the electric field creates. So my question to you now is to figure out what would the direction of this magnetic field be in the region of space in between the parallel plates. And the choices, as always, are going to be left, right, up, down, or into the page, or out of page for the magnetic field. Pause the video and see if you can figure it out. All right, so hopefully you got it. It's into the page. And the reason is because we need to have a force that pushes up from the magnetic force, which is going to be balancing out with the force from the electric field here. So those two will balance on the particle. And in order to create an upward force vertically up here in the positive y direction, you would need a field pointing into the page, because if you use the right-hand rule, if you recall, we point our fingers in the direction of the velocity vector, and then we curl in the direction or cross in the direction of the field. So let me just draw it out in three-dimensional space, since it's kind of hard to draw a picture of a hand doing all that. So here we would have our velocity vector going this way to the right. And then we would have our magnetic field vector going this way into the page. These are our three axes here. And then that would lend to a force. I guess I'll do that in blue here, I guess. A magnetic force vector right there. All right, so hopefully you can see that this is a right angle with the perspective there. And the magnetic force vector is always perpendicular to the plane that's formed by the velocity vector and the magnetic field vector as shown. Cool. Awesome. And let me just label these as well while we're at it, just so we have that magnetic force, and then we've got the magnetic field B, and then we have the velocity vector V. So you can see that plane that's formed between V and B, and then crossing from V to B with the right-hand rule gives us the magnetic force up. All right, now let's apply this. And what I'd like you to do is see if you can figure out some type of expression for the velocity of the particle. So you're after something, V is equal to some stuff. And what goes over there, well, I'm going to leave that up to you. You have some information here about the free body diagram, and you also know something about magnetic forces and electric forces and what those depend upon and the particular variables in those forces. So just apply that and see what happens, and you'll develop an expression for V that's actually pretty simple in the way it looks when you finish it, and it will be an interesting result as well. All right, so pause the video and see if you can produce an expression that would give us the velocity of the particle. Actually, it's just going to give us the speed. We know the direction is going to be to the right. The speed of the particle as it exits the field. All right, go ahead. All right, so to get there, you had to write an expression for the magnetic force, which is QVB sine theta. Angle between the velocity vector and the magnetic field vector is 90 degrees, so sine of theta is 1. And then we know that the electric force, the magnitude of it, is QE. So we're just working with the magnitudes of the forces here. We know that they're balanced, so the magnitudes of the forces must be equal to each other. Therefore, we can set them equal to each other. I guess I'll do that up here. So QE is equal to QVB. Interestingly, the charge cancels out. So we'll cancel out the charge, and we'll solve for the velocity. And when we do that, we get the velocity is the magnitude of the electric field divided by the magnitude of the magnetic field. And we call this a velocity selector. See if you can kind of figure out why that's the case. And it's a pretty simple result. We just have the magnitude of an electric field and the magnitude of a magnetic field with a division problem. And this will predict that this particle here with this speed v and this field E and then the magnetic field B, I should have written that down over here like that, we will for sure get this particle to emerge over here on the right as long as it has this particular speed, v. And that's why this is called a velocity selector. So for example, if we now, let's bring another particle over here, and I'll ask you a question. What if we had a particle, another positive particle here, we'll put it up here, and it was coming in at speed 2v. So something like this. What would happen to it? Would it also go straight through unaffected? Would it deflect up? Would it deflect down? This is a very important question. See if you can answer it exactly what would happen. All right, pause the video and give it a shot, and then we'll take a look. So to get the answer to this, we need to just look at each force. The electric force will not change. It will just be QE because we haven't changed the charge and we haven't changed the electric field strength in any way. So that doesn't change. However, the magnetic force, very importantly, does depend upon velocity. And this is quite strange, but it's how the magnetic force works. It depends upon the direction we're traveling and also how fast we're going. And in this equation here, the direction is, of course, taken care of with the sine of theta, and then how fast we're going is taken care of with the speed right here, v. So if we look at this, we have twice as much speed, 2v. Therefore, we would expect to get twice as much magnetic force. The angle is still 90 degrees, of course, so that won't change. So let's draw that in, and you would have something, a free body diagram that kind of looks like this, where you've got a much larger magnetic force. In fact, it would be Q times B, and now what would go in here would be 2V, or twice as much, so it would be 2QVB if we were parameterizing everything in terms of this other one over here, just QVB. And that should show you that we have a net force up, and therefore we would expect that this particle would have an acceleration up, and it would deflect that way. Maybe it would strike the upper plate, or if it was going really fast, it might emerge over here out on the right, but it certainly wouldn't be going straight like this. It would be moving at an angle now because of the deflection. So interesting question. Now, how could this be useful? Well, we now have a way to select the velocity of particles. So over on the left-hand side, you can imagine we have some source of charged particles where maybe it's like thermal emission, where you've got this electrode that's really hot or something, and you got particles being ejected off it at random speeds in random directions. And now what we're able to do is let all of those just kind of come into this region of space, and pretty much all of them, most of them, will be filtered out because they'll hit this plate or they'll hit that plate or they'll do whatever. But a very tiny select few of them will have the exact speed and direction, really just going straight in like this at the exact right speed to make it all the way through unaffected. And what that would mean then is whatever we see coming out over here, and we could maybe, I don't know, just like close this off or something with a little gap right there. And whatever comes out of there, we would know precisely how fast they're going. That's pretty cool. And we'll see what we can do with that here in a second. Now also notice that in this formula for the velocity selector, we don't see anything to do with mass. And also here, the forces, both electric and the magnetic force, don't have anything to do with the mass of the particles. So we could have two particles with unequal masses come through here, and we would see identical balanced forces up and down on those particles, and they would both fly through, as long as they had the exact same velocity, the correct velocity that we need. So we could get a particle of a light particle or a heavy particle going through here. So we wouldn't really know the mass of the charged particles as they emerge here, but we would know how fast they're going. So now you might be wondering, okay, well, wouldn't it be nice to know the mass of the particles? And the answer is yes. And how could we do that? Well, we can continue to use the properties of fields, specifically the magnetic field. So you hopefully would know that if we had a particle here emerging with some velocity like this going into this field, we've learned that this would now move in a circular path and specifically would form a semicircle here, and we know how to calculate the radius of that path, r. Let's just quickly do that. Sum of the forces in the radial direction is mv squared over r. And the only force in the radial direction is the magnetic force, qvb, sine theta, but again, the choice of the magnetic field here, B, is at a right angle with the velocity vector. So we can plug in qvb is equal to mv squared over r, and we get this to cancel. And we end up with a formula for the radius of a particle, a little box around this. And you can see it's the momentum of the particle, mv, divided by the charge of the particle times the magnetic field strength. So therefore, if we had two particles emerge out of this velocity selector with identical velocities, but one of them had a larger mass, where would we expect that larger mass particle to end up over here? We can see this particle, we'll call this the lighter one. It goes around in a circle, a semicircle, and it ends up right here. But if we had a heavier particle with more mass, where would it go? Would it end up, I'll give you a couple choices here, I'll give you three choices actually. Would the heavier particle end up here in a tighter semicircle? Would it be exactly the same, or would it end up out here in a much larger semicircle? Okay, so that's the question. Compare that, pause the video, and see what you think. All right, so if you look at this, we have a direct proportion with momentum. So the radius that this particle traces out will be directly proportional to the momentum, and then these are constants, q and b. It's the same charge of particle and the same magnetic field strength. We're making an assumption that it's the same charge here, and then of course they're both going in the same magnetic field. All right, so awesome. Now that we know that it's a direct proportion with the momentum and the velocity is the same for both, then it just depends upon the mass, and we see it would be a much larger radius because there's more mass for that heavier particle. So the correct answer, as we fill this in, would be, I'll draw another path here. Let's see if I can get this kind of right. It would just be a bigger semicircle, something kind of like that. So this would be the larger mass particle, and then this one right there would be the smaller mass particle. And then if we wanted to, we could put a detector there And if we put a detector, we could kind of separate particles out. So if we had a bunch of particles emerging out of our velocity selector that all had the same charge and same velocity, but they had different masses, if we put some like collecting device here, then obviously the heavier ones are going to end out further up here all together. And this is what's behind the principle of mass spectrometer, where you're able to understand and determine the mass of something that's really small by figuring out kind of where these things land. So you have to first you got to get them into this like diffuse form where you can allow these little particles, to move from the electric and magnetic fields here. But then you can detect that, and it's really really valuable. One example of that you might be interested in is very famous, and if you think about the uranium atom, you have kind of two isotopes. You've got 235 and you've got 238. Oops, 238. And the one up here, or this one here, is the one you want for enriching uranium in order to use that to convert to energy. You can do that for nuclear energy. You can, or historically, it was done in the 1940s in the Manhattan Project to build the first atomic bombs, as they're called. I guess nuclear bombs would be more appropriate for what specifically they're called, but that's how you can separate these two isotopes, which is really hard to do. Of course, you have to kind of like grind it up somehow and get it into a diffuse form, and then put it through a velocity selector, and then have that go through this little mass spectrometer over here, and you can start collecting U-235 versus U-238. Now, the process would be really slow. There's better ways to do it, but fundamentally, you could do something like this if you wanted to isolate a lighter isotope of uranium. All right, that wraps it up, and you can see how we can create a velocity selector and also have a magnetic field in a region of space to create a little mass spectrometer. One thing you might have been wondering about though is like, okay, so how do we like precisely get the electric field and magnetic field values so we can manipulate these small particles, right? Well, it's an interesting question, and we know that if we have, charged plates like this and we put a battery across that, a voltage V, and this is a distance d, well, there's a relationship that the voltage across the plates is equal to the constant electric field times the distance between the plates. So here's now a really easy way to get the electric field strength. E is the voltage across the plates divided by the distance, and these two things are able to be manipulated by like your hand. You can turn a dial on a power supply that would change the voltage across the plates, and you could also turn a dial that would precisely move these plates a certain distance, away. You could create some like mechanical contraption that did that. So we have macroscopic controls over here, kind of on the right, that are manipulating now these really small particles and the forces on those particles with precision. That's incredible. And you can also do that with the magnetic fields. We haven't learned enough yet about how you would do that. But you could create a magnetic field with a certain strength out of, iron, or like a big bar magnet or something like that. Or usually what's done is you would have an electromagnet where you could precisely control the magnetic field by using the current that's flowing through a wire. And we'll be looking at that shortly. So these microscopic motions of particles can be controlled through these kind of bigger scale things that we can actually touch as humans, which is really cool. Awesome. All right, I'll leave you with this final challenge. We won't solve this here, but imagine you wanted to create a system where you had a charged particle that would move in a spiral like this, and as it moved around, ultimately it would come out here moving really fast with a lot of energy. So it would start with very little energy at the center, and then it would come out here with a high amount of energy, or any energy that you want. High amount of energy. This is a very famous contraption that was created in the 20th century, and it was one of the first particle accelerators, and now we have much bigger particle accelerators in the world. But think about how you could create this. There's a really interesting design. It's an ingenious design for how to make the system actually work. And I'll give you a hint. It has something to do with both electric and magnetic fields. And we're looking at the system from the top down. Okay, so this is like the top view. You don't need to worry about gravity at all. You're just looking from above straight down, and we see a particle, and it just spirals out like that, and then has a lot of energy. And then we could fire that at something, and that has a lot of practical use, especially in medicine. All right, so I'll leave you with that little challenge to develop your own little particle accelerator using electric and magnetic fields, and then we'll see at a later time how to do that. All right, take care, and we'll see you next time.